We're very pleased to have Danny Goodman come and talk to us about deep learning. Danny is a consultant in data science and machine learning, most recently doing deep learning at MetaMind, and before that, more machine learning stuff at Metromile. So I'll just hand it over to Danny.
Thank you, Sunil and David. Good evening. Welcome, everyone. Tonight, I'm going to be talking about deep learning for technology companies. So a few things before I get started and jump in. I think you should know a little bit about me to understand the bias that I bring to the subject. I've spent my career in startups, most recently as vice president of platform at MetaMind, which is a deep learning company, and before that as director of data science at Metromile, which is a connected car and car insurance company in San Francisco. I'm a huge nerd at heart. My undergrad was in math, master's in computer science, and I'm a huge technology optimist. So the goal with this talk is to say something that will be relevant for everyone in the room, whether you're technical or whether you are focused on which products to build or the strategy of your company, and regardless of how much you know about machine learning. So there's a lot that I'm going to try to cover, so I'm not going to have time to go into detail on a lot of things. So the slides are actually posted online. If you have a laptop out, I encourage you to follow along. And many of the links are clickable, many of the images are clickable too. Actually, all of the links are clickable, many of the images are clickable too. It was posted to the meetup group, I believe. It's a drop, yeah. Okay. So why should you care about deep learning? The short answer is that it works everywhere that it's been applied. It's incredibly useful to all of these companies, which you'll know. And to go into a few examples, image recognition is perhaps the best known. On the left, you see an example of object localization and detection, which is where you take an image and identify the objects in it and put bounding boxes around each of them. And Facebook uses this to tag the faces in the photos that you upload, and it does a better job than humans can on that task. Deep learning does speech recognition. It's powering the Skype live translation service that turns your voice into another language, still in your voice, in real time. It does language understanding. So MetaMind and Alchemy API are two companies that will sell you deep learning-backed sentiment analysis APIs. And the sentence here is an example of the detailed sentiment analysis that you can do not just on a whole sentence, but on every subphrase of a sentence. So this film doesn't care about cleverness, wit, or any other kind of intelligent humor. So most of the subphrases here are fairly positive, as you can see, and it's only the negation of the sentence at the very beginning that changes its sentiment, and deep learning captures that. And you also see deep learning be useful in places that you might not expect, for example, in biochemistry. Kaggle ran a contest a couple years ago where the task was to predict the properties of new potential drug molecules, and the winning result came from Geoffrey Hinton's group. He's a professor at University of Toronto who's a deep learning expert and not a biology expert. And some of you, like me, might be surprised at the incredible hype and popularity that deep learning has achieved extremely recently. So why now? The first and foremost reason is processing power. So most of us in the room are familiar with Moore's law, which was the law that says the density of transistors on a chip will double every 18 months. And the important part, or the important consequence of Moore's law for business is that the cost of computing comes down. So at bottom, you see a graph of Amazon's server costs that they will charge to you. Amazon is known for being fairly aggressive on price, and so as their hardware gets cheaper, they pass on their savings to the user. And you can see that even over the last few years, the price has come down considerably. And deep learning is extremely data compute intensive. Secondly, only somewhat recently have we had tons of enormous labeled data sets, which is another thing you need to do deep learning. So every smartphone has a camera. Social media is full of raw text, and services like Mechanical Turk and Crowdflower make it extremely easy to label these data sets at scale. And finally, once we got these technological precursors in place, we invented better training methods that have allowed us to do everything that will follow. So for the rest of the talk, I'm going to go through the definition and history of deep learning. I'm going to talk about the fundamental concepts that make it work. I'm going to go through some uses and examples, along with some tips of things I think you should keep in mind if you're going to implement it at your own company. And I'm going to talk about some things I see coming in the future, both the near-term technology advancements and some of the farther-term effects of deep learning and AI more broadly. So you can think of deep learning as neural networks. So you see a cartoon example of a neural network, and here's a way you might use it. So you might take an image, let's say it's of a city, and we've blown up a section of the image so that you can see the individual pixels. We would represent those as numbers, which are the luminous intensities of the pixels. And each pixel value would be fed into an input neuron. And then what a neural network does is compute the activation of each neuron, pass that on to the next layer, which computes their activations, then passes them on to the next layer, which will output something that you care about. And in this case, what we care about might be whether we're looking at a picture of a city or an ocean. So quick terminology primer here. Machine learning is algorithms that learn from data. Neural network, it's a biologically inspired machine learning architecture that's made of basic units called neurons. So neural network is biologically inspired. Our brains are neural networks. The typical human brain has 100 billion neurons with 100 trillion synapses. And the important parts of a neuron for the functioning of a neural network are synapses. So neurons have links that come in that are called dendrites, and an axon that goes out. And where the axon of one neuron connects to the dendrite of the next one is called the synapse. These links can be either excitatory, causing the next neuron to fire, or inhibitory, preventing the next neuron from firing. And let's make a mathematical model of this so that we can have a machine learning method. So we can represent a cell as an enumerated list of synapses. Each one receives an input from the axon of a previous neuron. This axon is either stimulated or not. And then each synapse has its own parameter. This parameter controls the extent to which the synapse will excite or inhibit the cell. And as a biological neuron does, the inhibition or excitation from all the neurons gets aggregated together in a cell body, and if enough stimulation is provided, the neuron will activate and fire and send an output, an action potential down its axon. So here's an example activation function called a rectified linear unit. It's piecewise linear. Rectified means that we've cut it off at 0, and this is, the functional meaning of this is that an axon can't negatively fire. If it's not stimulated, it just doesn't fire. So this is a very simple and in many ways unrealistic biological model, but it's a very effective one that will be responsible for all the things we're going to see in this talk. The basic building block of a neural network is a layer, which is a group of neurons that have similar connections. So on the left, we see a network that has one hidden layer, and every neuron in that hidden layer takes an input from every neuron in the layer below. And we can arrange these however we'd like. So the network on the right has 2 hidden layers. Now, the cartoon network on the right is fairly small. It's only got 32 parameters, which is all pairwise connections between all neighboring layers. But realistic networks that do the things that we're interested in are actually enormous. So on the left, you see a diagram excerpted from the 2012 paper that made tremendous progress on the ImageNet dataset. So this is a dataset of thousands of object categories. They get very specific, down to what type of dog, what type of plant are you looking at. And in 2012, Geoffrey Hinton's group published a paper that got a huge increase in performance on classifying this data set. And it was the first time that deep learning had given the best result on this task. And they did it with a network that had 8 layers and 60 million parameters. So this large number of parameters is what's responsible for the processing and data requirements of deep learning. And so, why do we need so many parameters? What do they all do? We can get some intuition for that by looking at maximally activating inputs. So this is, you take one neuron somewhere in the network, and we ask what input image, for example, or whatever domain you're looking at, would maximally stimulate this neuron. And if we do this at the first level of the network, we find that what we learn are basic image features. So we find edge detectors of various orientations, we find color detectors in different locations, and so on. And if we go higher in the network, we find increasingly complex concepts represented. So this image that looks cat-like was shown in the New York Times in 2012 because Google found that when they took an unsupervised neural network and trained it on zillions of YouTube images, that it decided that cat was a concept that appears in YouTube, as we all know, but until then, computers hadn't. So brief history. The first mathematical model of neuron activation is written in the 40s, first multi-layer neural net in the 70s. There was a tremendous excitement about neural nets in the 80s, which was followed by an AI winter, which was a period when funding and enthusiasm for AI was significantly diminished, and that experience still colors the perspectives of many researchers who work in the field. There was a rebirth with statistical machine learning in the 90s. Machine learning techniques and applications proliferated in the 2000s. And deep learning didn't break out, though, until the last 5 years or so. This is when it started achieving state-of-the-art results in many of the applications that we're going to talk about. And the 4 professors who are credited with having invented most of how we do deep learning are Yann LeCun at Facebook at NYU, Yoshua Bengio at University of Montreal, Geoff Hinton at Google and University of Toronto, and Andrew Ng from Baidu and Stanford. So with this background, we're ready to define deep learning. Deep learning is highly compositional, differentiable machine learning models. So highly compositional means that each layer is a function of the inputs that are passed to it from the layer before, which are themselves a function of the previous layer, and so on. And so you have many nested function calls. And each time you nest an additional function call, which is equivalent to adding another layer into the neural network, you increase the complexity of the pattern that you can represent. So as long as all of your activation functions and parameters are differentiable, then you can compute the derivative of your output with respect to every parameter in the network. And it turns out that this is what allows us to train these millions and, in some cases, billions of parameter networks. So there are many different ways that people can arrange neurons in a network like this. The examples that we've been showing in cartoons are called fully connected, and they're called that because every neuron in a layer has a connection to every neuron in the layer below and the layer after. But there are some specializations, 2 of which I'll call out, that are very useful in particular circumstances. The first is convolutional neural networks. So this is where, instead of having the stimulation of this neuron in a layer be caused by looking at the entire image below. It looks only at a patch of the image. So for example, this patch might be a filter that detects edges of a particular orientation, and then we move this patch all around the image and generate an output that is the extent to which each location in the image contains an edge of that orientation. So that patch will result in one 2D slice of the next layer, and so there are many 2D slices that will make up this layer, and each different 2D slice is a different filter, the parameters of whom are learned. And so in this way, you can have extremely large input images and networks with very large representational power and still share parameters and learn them efficiently. So to give you some intuition for what this looks like, the top left is I believe, Chinese character. I don't know what it is, but I do know that these are Gabor filters, which are edge detectors in various orientations. And if we convolve or apply these filters all over this character, we receive the filtered output in these 4 boxes. So here, for example, we've applied the vertical filter, and you can see that we picked up the vertical lines next to this box-like part of the character, but we didn't pick up the horizontal line. And similarly, below is the horizontal edge filter. And if you take the information from these 4 convolutions and put it together, you approximately recover the original character. The other deep learning architecture that I'll call out is called a recurrent neural network. And you can think of a recurrent neural network as analogous to a hidden Markov model. So each vertical slice you can think of as a different time step. And let's focus on one for a moment. So this first slice takes input. In this case, it looks at an individual character. That input goes to a hidden layer, or a number of hidden layers, and that goes to an output layer. And now, if we were training a network on images, the next image that we looked at would be independent. But if we're looking at a sequence, for example, as words in a sentence are in a sequence, then the hidden state at the next time step should depend on the hidden state at the time step before. And so that's what a recurrent neural network will do. When we feed in the E in hello, the hidden layer takes input both from the E and from the previous time step. And so in this way, the hidden state learns to represent sequences in its vector space. There's a lot of innovation in network configuration, which I won't go into, but when the different networks become increasingly successful at some of the upcoming applications that we're going to talk about later, you're going to start to see them appear in open source software. So the hard part of deep learning is training the parameters, all 60 million of them. The intuition is that you're trying to find activation weights that fit the data, such that you can feed in whatever image you're looking at and have the desired classification come out on top. And this is the reproduced example of what the weights might have learned if you've trained a network well. If you make mistakes, you see sort of noisy or less clear learnings of individual neurons. And so the training process is to basically get here to where your neurons have learned interesting patterns that will cover your input data space. So how do we train? We start with an objective function, which is a numerical way to judge the output. This is an example of a softmax, which essentially assigns a probability distribution to a vector with the highest probability weight in the max component of the vector. And this objective function has the effect of encouraging the greatest likelihood of the correct predictions across the data set. So once you have your objective, you know at the output layer how you would like to change the outputs in order to make your objective function better. And you also know how you would like the inputs to that last layer to change in order to make the classification better. Now, what you do then is backpropagate that information to the layer before. Then the layer before knows how its output should change and can say how its parameters should change and how its input should change to achieve that desired output. And if you continue to propagate this information back all the way through the network, then eventually the network knows the derivative of its output with respect to every parameter. And once you do this, you can use any of the standard gradient-based learning methods. So when you build a network, your choices are the hyperparameters. Usually, the network architecture and the objective function are fixed by the application that you're working on. And then what you get to choose is the architecture, number of layers, number of neurons, and the learning algorithm, like stochastic gradient descent or LBFGS, which is an approximate second-order method. And these can have many parameters themselves. All right, so when should you use deep learning in practice? It needs tons of data to fit all the parameters. And as a rule of thumb, I recommend not using it unless you have at a minimum hundreds, probably thousands of labeled data points. The data should contain a complex and hierarchical structure that matches the structure of the model itself. For example, images, text, speech, and video are like that. But if you don't, I'd recommend other methods. For example, one of the applications we worked on at Metromile was understanding the instantaneous fuel consumption based just on velocity and acceleration. And a physics-based model was more appropriate there than deep learning. So how can you know what the opportunities are in your business to take advantage of deep learning? There's a question that I like to use, which is, what would you do with 10,000 free interns? So these are folks that you don't have to pay, you don't have to feed, they don't have to go home and sleep. They're untrained humans, but they can understand images and text like anyone you would find off the street and reliably follow simple instructions. And so anything that these folks could automate is a candidate for deep learning to help you automate. Examples. Facebook's tagging in photos, looking at photos and judging what's in them and where. Customer support. Customer support is not the most loved industry in the Valley right now, but if we can do better triage and filtering of incoming queries, which deep learning makes possible, I think we can improve that experience a lot. And finally, there are many unexpected applications of photos. For example, folks who do insurance rating want as much repeatable and available data to enter into their rating model as possible. And one, believe it or not, relevant rating factor is how many trees are in a property that you're considering insuring. So this labeled data can become an enormous competitive advantage. So how do you get it? One way is to have internal folks at your company label it. We did this at Metromile and MetaMind. And to make up some rough numbers here, if a person can create one label a minute, let's say, classify something and put a bounding box around it, then 2 people can generate 1,000 labels in about a day. And that's a really boring day, to be sure, but it can be really valuable to the company over the next years. Another approach is to outsource the labeling to services like Mechanical Turk and Crowdflower. And LinkedIn famously used this several years ago to take the different ways that people would enter their company name and merge them together. And this is extremely scalable, but it can be fairly difficult to set up in such a way that you get high-quality labels, because there's a problem of bots and spammers on these services. And so you need to do things like be sure to have many people rate the same image and check that they give the same results, randomize the multiple choice order of the questions that you give them, and so on. And finally, you can almost always use approximate labels, which is if there's something that you want to predict or measure that you don't perfectly capture, there is some kind of proxy for it available in your data set. For example, if you want to predict the effectiveness of a sales call based just on its transcript, well, that might be a hard number to go back and label, and maybe you don't want folks reading tons of transcripts to label them. But if you're using a CRM, then you know what the outcome was of that entire customer interaction. And so you can use an approximate label, which is, well, was there a follow-up call? Was there eventually a sale? Something like that. So if you want to use deep learning, how do you do it? So the fast and cheap way is just to use open source, and we'll talk about some open source packages next. If what you want to do with deep learning is absolutely core to your product, or if you're a big company with a thriving technology practice, typically there's so much value in it that it's worth it to do it yourself, meaning you hire deep learning experts, you get into the nitty-gritty of the backpropagation, and you write your own code. And another way to do it is just to buy it. And here's a sampling of companies that will sell you deep learning in different application areas. So here are 3 of the most commonly used open source deep learning frameworks. Caffe comes out of the Vision Group at Berkeley. Torch is a popular open source machine learning framework to which Facebook AI has added deep learning capabilities. And Deep Learning for J is a Java-based deep learning framework. So there's actually tons of these right now, and I would bet anyone that you can find an open source deep learning framework that works with your software language and technology stack. I also recommend that if you're starting to use deep learning, you start on AWS. So the deep learning training jobs can take minutes to, well, on the very short end, to weeks. And that makes it inconvenient to do on a laptop, although I do recommend that all your developers have laptops with GPUs so that they can at least compile the code and test small examples. It'll make development a lot faster. So you can train and test on Amazon's EC2 servers. They have GPU servers with NVIDIA GPUs. If you want to be as agile as possible and just get off-the-shelf on-demand servers, it'll cost you a bit under $500 a month per server. If you know that you want servers for the foreseeable future, you can get them for $200 a month. And if you're only doing research applications that are not production critical, you can get them much cheaper by bidding on what are called spot instances, which are Amazon selling their excess unused capacity. And so there's a running real-time auction for these servers with prices that are significantly cheaper than the on-demand instances. The drawback is you can get interrupted if the price goes above what you bid. So these data sets are frequently quite large. So I'd recommend storing your data on Amazon's Elastic Block Storage, which is essentially a hard drive that can be up to 16 terabytes. You attach them individually to machines that you're interested in. They also have an Elastic file system, which is in preview. And so if you want multiple machines to be working on a data set in the same place, that's an option to try to get into their preview. And finally, there are lots of different ways that you can have a workflow to submit training and inference deep learning jobs. Again, I recommend using Amazon services for this because they're essentially infinitely scalable, reliable, distributed, and consistent in the ways that matter. But it's also fairly easy to set up your own. And I've worked with Mesos and RabbitMQ before. You can just install those on whatever EC2 servers you're using. Now, a lot of folks will be tempted to buy and co-locate your own hardware for deep learning. It can be cheaper at scale in the long run, but it's a huge hassle. And just to enumerate the ways that it is a hassle so that you can make sure that it's worth it before you make the mistake of doing it. there's the obvious negotiation and upfront purchase and install of all the equipment, but there's a lot of stuff that Amazon handles for you that becomes a pain in the long run that, well, you'll have to do yourself if you co-locate. A few tips on how to run a software shop doing deep learning. So first, I would automate and version control everything. That means every time you set up a new server, make sure that there's a script somewhere that captures how to do it. Make sure you have a one-line deploy process, and that whatever you use to submit, train, and test jobs is equally easy, that there's a command line submission process, for example. And here are some tools that you can use to set those things up. Before going live, these are extremely complicated systems that are very resource intensive. So I recommend setting up monitoring and logging. I've used all these services before. They're all great. And finally, don't do anything yourself unless you want to make Satan dance. Network file systems, for example, are really hard to work with. And there are lots of other architectures that will achieve the same goals. So some further software tips. Since the applications, your software applications that do deep learning are going to be very complicated, time that you spend up front designing them well will be worth it. That means figuring out how to make them debuggable, modular, extensible, etc. And 2 sanity checks that I'll call out in particular when you're developing these applications. One is called a gradient check. So you'll remember that backpropagation means computing the derivative of your output with respect to every parameter in the network. You can numerically check that you've got the right derivative by wiggling the parameter a little bit and checking that the output varies as you expect it to. And finally, you want to make sure that you can overfit a small sample of your data. So ImageNet might have millions of images, but before I spend several weeks of runtime training a network on ImageNet, I'd first like to take a sample of, let's say, 10 or maybe 100 images and make sure that my network with 60 million parameters can get 100% on those images. And if it can't, there's something wrong, and it's much easier to diagnose on runs that will take a minute than on runs that will take a month. Also, general machine learning good practice is splitting your data into different sets for different purposes. So the training set is the one we're all most intuitively familiar with. This is the data that you backpropagate on and use to fit the weights of your model. A validation set can help you decide between different hyperparameters. How many layers do I want? How many, what learning parameters should I use? And it's important to have a validation set as an arbiter because different hyperparameters will be over-optimistic to different degrees on your training data. So you can't look at the training performance as a good reflection of which model will do the best. And then finally, you frequently want a separate test set. So before you launch a model live, you want to understand how it's going to behave in the wild. And the only way that you can do that is to have a fresh set of data that has had no input on what your final model will be. Some intuition for a validation data set. Here you see 2 nearest neighbor classifiers. This classifying based on your single nearest neighbor, and this classifying based on the plurality vote of your 5 nearest neighbors. And so the 1NN classifier essentially gets 100% on the training data, but we wouldn't expect it to get 100% on new data. The 5 nearest neighbor classifier doesn't get 100%, but might actually do better in certain situations because it's able to ignore random events and noise. And finally, k-fold cross-validation is another standard machine learning trick that trades extra processing time for effectively having more data. And so here you can take validation and training data in a large chunk, divide up that combined data set, and one experiment on each chunk of the data where you hold out that chunk, train a model on the remaining pieces, and do inference on the validation chunk for that experiment. So each of these experiments will give you a slightly different performance. You can average them together. And the advantage of doing this is that all of this data gets to be used both to help you train and validate. So you did 5 times as much computation, but you got effectively twice as much data. So here is a quick example taken from the Caffe repository on a data set of 10 categories of images. So the images are quite small, and if they were blown up larger than this, you would immediately see the pixels in the images. It's an example that comes bundled with Caffe, and if you can see this, the top left is the bundled code that runs it. So it's essentially 2 commands, one which trains it for a bit with one set of hyperparameters, another which trains it for a bit with another set of hyperparameters. This is what a hyperparameter file looks like. Says what the network topology is and some of the training hyperparameters like number of iterations. And then here's what a network file looks like. It just defines the layers that you want in your network, and then Caffe will take care of everything else for you. So this network on this laptop trains in about 20 minutes and gets 75% accuracy on the test set. And just to step back for a moment, in 2007, I took a graduate statistical machine learning class at MIT. And this was something that the most brilliant minds in the field in 2007 didn't know how to do. And now it comes bundled in open source software that runs on my laptop in 20 minutes. So I think that's incredible, and that's a personal example of how deep learning has made a lot of progress over the last decade. All right, so now some future thoughts on what's coming down the pipeline. So in the near term, I think deep learning is going to continue to be effective. In the medium term, I think all of this automation is going to have economic and social effects. And in the long term, we've heard about the safety concerns that people have. So one of the reasons that those of us in technology, I believe, are so well paid is because we invent ourselves into all the jobs we have by taking the best ideas in the field and open sourcing them and sharing them with each other so that we can all be extremely effective and productive. And I think this same thing is happening to deep learning. And to give you one example of this pathway from research to open source. So in 2012, Geoff Hinton's group first published a tremendous improvement in image classification on the ImageNet dataset using deep learning. And the next year, Google had implemented it in a proprietary way for image search, and it made a much better image search. And then the following year, the Caffe framework was released that had the same algorithms. So this funnel happens everywhere. And as a result, I think deep learning is not going to be a competitive advantage, the fact of you doing it. And the question is simply, where do you want to be on the adoption curve? Is it worth it to your business to be an early adopter, or do you want to wait? Here's a glimpse into some applications that are in the research pipeline right now that I think we will have solved reasonably well, probably in 2 years, and that will probably be open sourced in another 2. One of them is question answering. This comes from a paper from Facebook Research. For example, what American cartoonist is the creator of Andy Lippincott? And it would return a triple Andy Lippincott character created by Gary Trudeau. So the ability to ask in natural language questions of a structured knowledge base and get structured answers back. And the bottom, conversation, which is an agent doing automated technical support for a human, comes out of Google Research. We're also going to be able to generate examples of data points that are realistic in a variety of domains, and some ways that we're doing that. It turns out that this is already how we do our state-of-the-art machine translation. So if we want to translate English into French, we first train a recurrent neural network on English sentences, recurrent neural network on French sentences, and then for each pair of sentences that mean the same thing, we further train those networks to make the hidden state for those sentences as close together as possible. And then what we do when we want to translate a new sentence from one language to the other is we input an English sentence into the network, get the final hidden state, move that hidden state over to the French network and say, okay, go French network, give me a sentence. And then that generated sentence is the French translation of the English sentence. And that's our state-of-the-art result in machine translation. So that means we're already pretty good at generating sentences. Google has an awesome paper that came out within the last year. And actually, I'd like to show you a demo of this, because it's so cool, where they trained a network that learned how to create handwritten digits that look realistic. And so you can see the network kind of going back and forth and drawing them. So, thank you, YouTube. I find that incredibly cool. And we can also do this in a cross-domain way. So there are papers that will take an image and generate a caption or a one-sentence description of the contents of the image. And finally, we are very close to doing general behavior learning in supervised environments. So these are environments where you get an instantaneous score that tells you how well you're doing in the environment, and having the agent automatically learn how it ought to behave in that environment. DeepMind had the most famous example of this by creating a network that learned to play a variety of dozens of Atari games, most of them at superhuman level. So the setup was the input to the network was just the pixels of the game's display plus the instantaneous score. The output was just the available control actions. And so you start a network training in the beginning as just kind of randomly jittering around, and you leave it training for a while, and eventually it starts to play the game in a decent way. And if you leave them training for a long time more, it frequently will discover the best possible ways to play the game, with superhuman control, because computers run faster than our brains. And here, for good measure, is a link to a JavaScript demo of Deep-Q learning, which is the algorithm that does the DeepMind work. And this will let you see in a browser what it looks like as the behavior improves over time and develop an intuition for what's going on. So in the medium term, I think that all of this automation and all of the great work that we're doing as an industry, while it will have tremendously good effects, also carry some economic and social risks. And I'd like to highlight one example. And while I am not an expert in economics or public policy, I hope to convince you that these questions are important and that there are things that our industry can do and that we can all do as individuals. So it turns out that being a truck driver is the most common job in most states. The CEO of Uber says that he doesn't want to pay all the drivers for the Uber cars. They just bought the entire robotics group from Carnegie Mellon University, which is one of the top deep learning departments in the world. And they're working as hard as they can to make self-driving cars a reality. And so some extremely smart people think that the economic challenge of the future is not going to be feeding everybody like it has been in the past. It's going to be making sure that folks have good jobs. So what can we do about it? I think there's actually a lot that our industry and we as individuals can do. So first, there's a big structural mismatch in skills right now. For every software engineer, there's something like 4 open jobs. And our industry, technology, is working reasonably hard to try to fix this. I've highlighted 3 examples of companies that are trying to train folks to take some of these open jobs. And I do think that lifelong job training for many folks is going to become a part of how we live, and that our entrepreneurial spirit can help that happen. And finally, I think there's a lot that our government can do, and I've highlighted a very conservative, a middle of the road, and a very liberal public policy proposal that addresses this. And so I hope that wherever you are in the political spectrum, you will make this something that you care about. And finally, there's the question of what happens when artificial intelligence is smarter than us. And let me be clear, we are nowhere close to this. AI is dumb, but it's getting smarter, and there, as far as we can tell, is no physical or algorithmic reason that it will not be smarter than us eventually. I believe it's going to happen in my lifetime. And so what happens when our computers are smarter than we are and we can't necessarily control them? We don't know what those smart machines are going to look like, and so we can't necessarily engineer them for safety right now, but there's a lot that we can do. One is, I think, we can be responsible by understanding the issue and the risks. Here's a blog post or a book, depending on how much time and interest you have to explore the subject. And these are the best that I've found. And there is also a fair amount of interest in the research community in exploring these questions. Elon Musk recently gave $10 million of his personal fortune to support research in this area. And the funded grant proposals were recently announced, and it's very interesting work. And so I encourage everyone here to be interested in the results when they're announced just for their own sake. So in summary, deep learning is basically generalizations of neural networks. It's very hard to do because it takes tons of computing power, tons of data, but it works everywhere. And so it's a very valuable skill set to develop personally and at your company. I recommend that you label your own data, which can become a huge competitive advantage, and use open source deep learning software. And I also encourage you to think, talk, and read about the impact of AI and automation on our country and the world. Here are some links that might be helpful to you should you wish to continue to explore. And at this time, I'd like to take any questions.
Hello? Oh, that works fine. First question. Somebody raise a hand. Here, you're nearby.
It's sort of confusing. I mean, deep mind versus meter mind, different kind of company. I was thinking, your former company was acquired by Google. My question is, deep learning is relying on big data. How about if my application is short of big data? There's no sufficient data.
Sorry, so to make sure I understand the question, it's what happens if your application doesn't have enough data for deep learning?
Yeah, that's right.
Right. So there are two basic options. The simple option is, well, probably use another method, but actually there is something that deep learning is discovering how to do, which you can think of as transfer learning. For example, let's say you want to classify some new type of image, and you don't have 10,000 labeled examples. What you can do, so most of the parameters in a deep learning network go towards learning the low-level patterns, and so you can reuse those low-level patterns from another domain. For example, you can train a huge deep network on millions of ImageNet images, and then just add a new classifier on top to classify the few images that you have available in your domain. So you can't do that in every domain, but if you want to use deep learning in an area where you don't have a lot of data, that's what you can do.
Giving you an example, like Google search history, right?
Sure.
If Google does not have sufficient search history, my search history, it'd be very hard for them no matter what kind of learning model they're using. It's hard, you know. So I'm just curious, you know, you're talking about in image domain, so you are artificially create image or you are extracting the feature from your artificial images?
Right. So two parts to that question. First, in the example of an individual search history, while you're correct that it would take thousands of individual actions to train a model on what an individual does, you can still get lots of supervised data by grouping individuals together. And you might put 1,000 individuals into one group and train on all of them. And then you can still predict, based on, let's say, the text of a single search or only a few searches, which group a user belongs to, and then look at the attributes of that group as a whole. In the image example in particular, so recall that when you train a network, the neurons in the middle of that network learn representations of interesting concepts or features of the data. And so if you do the act of training a network on ImageNet and then just slapping a new classifier on top, what you do is, so you train the network on ImageNet, then all of the neurons know the kinds of patterns that appear in general images from these 1,000 categories. And then if you take your handful of images, let's say 10, you would run inference on those 10 images. And then at the top, maybe the second to last layer of the network, you get some representation of those things in a high-dimensional feature space. And you can train a new machine learning classifier on that representation. And so the pixel representation of those images will be basically useless from a machine learning perspective, but assuming the same type of information that's relevant to the ImageNet classification is also relevant to the classification that you want to do, those ImageNet features will be much better than nothing. So you can, that's transfer learning.
Hi. So I have two questions. One is it clear that like deep learning is principally supervised learning, so it's only suitable for building classification models, right? In other words, can you cite an application of this in recommendation systems?
Right. It's a great question. So no examples in recommendation systems come to mind offhand. It doesn't mean there aren't any. I would say that while all of the applications that I discussed were supervised learning, deep learning is also useful for unsupervised learning. So one example of that is for noise reduction, compression, and so on. And a model that does that is an autoencoder. So let's say we take an image, and so we have a network where the first layer is just the input pixels, and we have a hidden layer, and then the output is the same size as the input, so the number of pixels. And let's say we train this network so that we want its output to be the same as its input. Well, you might say, well, what's the value of that? I've just created the identity function. Well, it turns out that if the hidden layer is smaller, and frequently it's much smaller than the complexity of the input space, you can still reconstruct most of the output image, but what you've done is extracted a representation of your image that is much sparser. And so in that way, deep learning can also be used to identify interesting features of an image, things like principal component analysis and so on. And so you could feed that reduced representation into any of the standard recommender systems.
Another question, in terms of implementation, are you aware of Spark being used for this rather than coding it in whatever you were showing?
Yeah, it's a great question. I don't know examples personally, but I can't think of any reason why it would be particularly hard to do on Spark.
Thanks.
First of all, congratulations, Danny. It was pretty inspiring. I have two questions. First, how do you actually use deep learning for MetroMile?
Yeah.
Because you said something about use a simple physics model.
Yeah.
And the second one was, why is so important the derivative of the output, right?
Yeah, absolutely. So the first question, we didn't actually do deep learning at MetroMile. We did data science, and so many of the engineering principles that we talked about were very useful there. The physics-based model that we use was ended up just being a regression. So I highlight that as an example of where deep learning wasn't appropriate, because there is a simple and direct and physics-based relationship between the output of sensors that come out of the car and the instantaneous fuel usage. And so that's an example where other methods were more appropriate. So your other question was about derivatives and why they're so important. So the hard part in any of these models is tuning the parameters. Am I addressing it? Okay. So when you start, you typically initialize the parameters randomly, and then you have to continue to update them in some way to get them to represent your input correctly. And well, how do you do that? Well, it turns out that if you define an objective function that you're trying to optimize, you can think of each individual parameter as a component of a vector. And so then you have a vector of all the parameters in some extremely large dimensional vector space. And then what the derivative tells you is the direction in that vector space that you can go to most quickly improve your objective function. And so that's why you want to backpropagate the derivative.
Have you seen any work related to applications of deep learning in a case where the classes are highly unbalanced? So say, you're looking at YouTube videos and it's all cats and there's one dog. How does deep learning handle that sort of unbalanced situation?
Yeah, it's a good question. As far as I know, there are no special particular to deep learning techniques for doing that. You do the standard machine learning technique, which is most objective functions will implicitly weight all of your data equally. Now, let's say you're in an application where you have 1,000 cats and one dog. Probably you don't care 1,000 times as much about cats going forward than you do about dogs. Let's say maybe you only care about them equally or 10 times as much. And so then the standard approach is to re-weight your data in your objective function to match how much you care about each class in real life. And so you won't be able to do a great job on the dogs if you have only one example, because you won't get the full variety. But by re-weighting each of the examples in your objective function, you can still make sure that you can still tilt your classifier to have the right priorities.
Related to that,
Yeah.
So you mentioned that deep learning tends to be useful for hierarchical problems.
Sure.
Have you seen it used in a time series domain? So it's like network traffic or clicks on a website in a sequence where, maybe there's a hierarchy there, but it's not clear what it is from, a human perspective.
Yeah, absolutely. So our senses and our brain wiring is, an accident, an outcome of what senses happened to be useful to surviving on the savannah 100,000 years ago. And so the fact that the hierarchical structure in some new domain might not be apparent to us doesn't mean that it's not there, as your question implies. And so as long as there is structure and you can construct a net that you might have to play around more with the network architecture, because we are better at designing nets when we have an intuitive understanding of what the structure ought to be like. But there are examples where the drug discovery, for example, it is not intuitively obvious to at least the group that developed the network what the hierarchical structure is in molecules, and they were still able to build a net that did it well. And speech data is essentially a time series, and deep learning gets state-of-the-art result on speech data.
So, two questions. First question is, you mentioned that you didn't see this thing as being a competitive advantage, but on the other hand, having labeled data, if it's proprietary and you wind up having this stuff come out the back end of it, that seems to me to be a proprietary advantage. What am I missing?
So you're absolutely right. What I meant in particular was that the deep learning algorithms themselves are not a competitive advantage in that they are going to be open sourced, but that your data is a competitive advantage precisely because you own it and you can do deep learning on it.
Okay. And then the second question I've got, again, kind of relates to the young lady's question. You touched on it briefly here with respect to the cancer stuff. I'm sorry, with respect to the drug discovery stuff. The drug discovery was that biological slide that you mentioned earlier in your presentation.
Yeah.
And again, you're interested in, you talk about the fact that you could deal with hierarchical, complex data. This is the stuff. What is the measure for that exactly? I mean, what's fed in there? Is it a signaling pathway? Is it a molecular structure? What is it that determines whether something is hierarchical and complex?
It's a great question. I'll make a physics analogy here. So the short answer is, I don't know, but that these techniques work so well on every area where we do see hierarchical data that you can almost start to use whether the technique works at all as an indicator of whether there is hierarchical structure. Yeah, exactly.
It is 5 minutes till 8, so let's take another 5 minutes worth of questions, then we'll do the random access. Looks like you have one, and then there's one there, and see how it goes.
Danny, I have a question about the recurrent net that you show us. I'm wondering, the net actually is you have a series of backpropagation nets working parallel, and each of them try to recognize one character, right? I remember you show us the picture for recurrent net.
Yeah. So is the question, how does backpropagation work in a recurrent net?
I'm wondering the structure of the recurrent net you show us. Yeah, here we go. So you have a number of backpropagation net working parallel, right? Each of them try to recognize one of the characters.
Oh, no, it's different. So are you familiar with the hidden Markov model?
Say it again, please.
Hidden Markov model?
A little bit, not much. Could you introduce?
Yeah. So I don't have time to explain what a hidden Markov model is, but the right way to think about this is each time slice of this,
Yes.
this is essentially one model that you have one instance of, and the internal state of this model is changing in time. This
Okay.
is not 4 different models that you see here. It is one model, and first you feed in an H, and then you feed in an E, and then an L, and then an L.
Yeah.
And the internal hidden state is changing at each time. And when you do backpropagation, so your objective function, your output, will depend on the output at each time step. And so this makes backpropagation a little more complicated because when you change one of the hidden layer parameters, that affects, in a normal network, you just propagate that forward and that affects one data point or one image at a time. But here, changing one parameter affects the output at every time step. And so actually your derivatives can get very, very large by the chain rule, by the product rule. And so one of the tricks that people have for these things is to limit the gradient so you don't get numerical blow up. But it's a single model, and so you're not running multiple copies of backpropagation, you're running one backpropagation on this network.
Or just one?
Just one.
Okay, thank you.
Deep learning has been heavily applied on the computer vision problem like ImageNet, LFW, everything, where you have the input in the matrix format, row by column, and you do the convolution. What if I have my input in a vector format like matrix value or log data? How do I do the convolution with those?
So the question is, if you're working in an image problem, but your image comes in a vector format instead of a matrix format?
In the matrix format where I have the rows and column, and then I can do the convolution easily with the some filters on top of that? And what if my input is some vector, like speech, which would have just 10 dimension?
Oh, I see. Right. So the dimension of a convolution, I see no reason why that can't vary. So an image is a two-dimensional input, and you can have a two-dimensional filter that you can volve around. But if your input is inherently one-dimensional, I see no reason you couldn't still have a convolutional filter that you slide along your one dimension.
Okay, so do I need to pad some information or just pass? Do I need to pad the information with the vector or simply passing will work?
I'm sorry, I'm not. So you would have the same types of choices to make as you would for an image network. Namely, how many different independent filters will you have? How big will each filter be? And then you just convolve them and learn the parameters the same as you would for a two-dimensional network, except you only have one dimension.
Okay.
Hello? There we go. So let's take one more question, and then we're going to do the random access. So if anybody's interested, if anyone wants to do the random access, why don't you come up to the front and get ready for it?
Just one follow-up question was the recurrent neural networks. So there has been some frameworks, like you mentioned, like Torch for images and those kind of convolutional neural networks. For ones that's targeting natural language processing, I'm aware of a few, like the Word2Vec and Glove and those kind of existing software. Is there any for recurrent neural network that you're aware of, or some upcoming work that we should be watching?
Yeah.
You know, we got the better stuff around the corner.
Authors in the field will frequently open source their code. I haven't used any personally, but I'd give you 10 to 1 odds right now that there are.
Thank you.
Okie dokie. So that's a wrap up for Danny. Thank you very much.